Welcome to the lecture series on PN Junction Diode, and in this lecture we are going to discuss about the diode capacitance. So PN Junction Diode, it has the inherent capacitance, and due to its physical structure it will have the two parallel plates, positive and negatively charged, and in between there is dielectric. How exactly it works, I'll be discussing that in the subsequent slides. And however, this diode is primarily known for its ability to conduct current in one direction and block in the reverse direction, but it also possesses certain amount of capacitance, and nowadays we are having uh, this diode as capacitor. It is gaining popularity and gaining wide application areas, diode as capacitor. Now, diode capacitance, there are two types. In forward bias, we have diffusion capacitance or storage capacitance. So, this is denoted as CD. In the reverse bias, we have transition or depletion capacitance and popularly denoted as CT. Now, what is transition capacitance? It is diode during the reverse bias. We have this dielectric here, this recombination junction part where the recombination is taking place, that is working as a dielectric. So this is something insulator type of material we have, and here we have the positively charged material, here we have the negatively charged material. So you can say this is our p side, this is n side. So here this area, these two are working as a conducting parallel plate. Now here if we try to find the value of the capacitance CT, so it is given as epsilon A by W. Now what is epsilon? It is the permittivity of the material, A is the cross-sectional area of the junction, and W is the width of the depletion region. Now depletion region, as I have mentioned, it is acting as a dielectric, and here normally this value CT is very small. It is almost equivalent to 20 picofarad. And now if you apply more reverse voltage, then this dielectric portion, this will become wider. And since from this equation you can see that if width increases, then the capacitance value will also decrease. So it is 20 picofarad or even less we may get out of this transition capacitance. So we can say that the capacitance, transition capacitance, is inversely proportional to the width of the depletion region. That means more the reverse voltage if we apply, this width of dielectric material or the uh, junction here, this depletion region width, that will increase. So this equation implies that CT is also inversely proportional to the reverse voltage. Next we have diffusion capacitance. So diffusion capacitance is much greater than the transition capacitance, and diffusion capacitance generally ranges up to diffusion capacitance, it can go up to say 1000 picofarad also. So that means we can get uh, the diffusion capacitance in the microfarad range as well. And here it is given, it is the capacitance during the forward bias. So once we get this knee voltage crosses, so this side we have the diffusion capacitance. So diffusion capacitance is basically CT plus CD together. We can write, since CD is much greater than CT, so we can write this entire thing, whatever we are getting during the forward bias, is the diffusion capacitance only. Whereas during the reverse bias applied, there we do not have any diffusion capacitance, we have only the transition capacitance. So mathematically it is given as CD as dq by dV, where dq is the change in the number of minority carriers stored outside the depletion region when a charge in voltage across the diode dV is applied. And what is this tau in equation 3? So equation 3, tau is nothing but the mean lifetime of holes or electrons. Otherwise, eta we already know. So it is 1 for germanium and 2 for silicon. Vt we know it is the temperature equivalent voltage or thermal voltage also. And Id is the diode current. So if all these values we have, then we can find the diffusion capacitance. And as I have mentioned, diffusion capacitance is much greater than the transition capacitance. So if we draw the equivalent circuit in terms of capacitance of a diode, so we can say that the diode is in parallel with the transition capacitance and diffusion capacitance. So this is the equivalent circuit of the diode in terms of capacitor. So you can solve this numerical. So if eta is given as 1, Vt is given at room temperature, Id value is given and tau value is also given, then you can find the diffusion capacitance. So here I have already solved and answer I have given. So this is for your practice. And second problem, here I have not given the answer. All the values of eta, Vt, Id and tau, all the values are given. Simply you just put in equation number 3. That means this equation, all these values are given here. So you have to find the diffusion capacitance. And after solving question number 1 and question number 2, please compare it. And you can keep these eta values same for both the cases also. So if material changes, how it differs, and if we have the same parameters, if tau changes or id changes, keeping all other parameters same. So this kind of analysis you can do, and you can comment here what you are getting. Now if we see the application part, so first of all, in high frequency application, diode as capacitor, that is having huge application, especially in the radio frequency circuits as switching or any other cases. This diode capacitors are widely used. Then in voltage controlled oscillator, once again in the communication device, in any type of receiver, these voltage controlled oscillators are used for tuning purposes. And here also diode as capacitance it is used. And here the for tuning the receiver, this value, capacitor value, may be changed by applying the proper voltage, and accordingly resonant frequency of the oscillator can also be varied. Then it is used as frequency multipliers. So diodes with non-linear capacitance characteristics, so such as varactor diode, which is a very popular diode, varactor diode, and these are used in frequency multipliers. So by changing the bias voltage, capacitance of the diode can be adjusted and enabling the multiplication of the input frequencies. Then we have analog and digital modulation. So in analog and digital modulation also diode capacitors are used. And sample and hold circuit. So when we are talking about the sample and hold circuit, so from here onward your digital communication, then signal processing, all these things are starting from this sample and hold circuit. So in sample and hold circuit also we require capacitor, and normal capacitors whatever available in the market, these are getting replaced in the commercial circuits with the diode capacitance. So here we end our discussion on the diode capacitor. So join me for the next lecture. Thank you.